Willie, thank you for a very nice introduction, and thank you all for coming today on Sunday morning, 8:30 a.m. Maybe you guys are as jet lagged as I am, and this hasn't been so painful, but I'm extremely grateful that you all came along to listen. So yes, I've been working in a kind of augmented and virtual reality devices for some time. I spent 5 years at Microsoft, where I spent a lot of happy times working on HoloLens 2, holoportation, face tracking. And 1 year ago, I moved to Tavo Bila's team in Google, where we're working on all sorts of digital human things for augmented reality and virtual reality, including synthetic data. So this is a story that starts and ends with gaze estimation. So you heard, I did gaze estimation in my PhD, and it's going to take a few detours on the way. And when we think about synthetic data, it's nowadays, I think, with all this amazing progress with machine model architectures, the biggest problem you have isn't choosing the right model, is actually finding the right data. And you can label that data, but you can also render data using computer graphics, and that's what synthetic data is. So I find this is a really interesting time to talk about synthetic data. So over the last few years, I think we're starting to see a bit of a paradigm shift. I remember the last big conference I went to before COVID. So that was ICCV 2019 in Korea, which was an amazing location. That was really great. And there, during a workshop on hand tracking, I saw this slide, and it said something like, synthetic data does not equal real data. And the presenter said, everyone knows synthetic data isn't as good as real data. You could never get something to work that well with just synthetic data alone. And this was not a controversial statement. So the whole audience nodded their heads and were like, oh yes, that's true, that's true. And there's always issues with the domain gap, and performance and training with only synthetic will never work. So I was sitting in the audience, just like you guys are today, bemused a little bit, because at that conference, for the first time, we were demonstrating HoloLens 2, including this hand tracker that I've been working really hard on. And it wasn't public at the time, but this had been trained using synthetic data only. And although bemused, I also empathized with the presenter, because making good synthetic data is really hard. It requires skill sets quite different to those of a typical computer vision researcher or software engineer. And although, at Microsoft, we managed to ship several products already with synthetic data like Connect and HoloLens V1 and HoloLens V2, we're still writing the cookbook, so to speak. What recipes work well and what recipes don't, which are dead ends. So in this talk, I'm going to share with you some of my favorite synthetic data recipes, starting with synthetic data for gaze estimation in my PhD, which I worked on a long time with Tadas, who I'm very glad has joined us in the audience. And then moving on to hand tracking for HoloLens 2 and a bit of body tracking and face tracking, where finally, again, as we do face tracking, synthetic data will help us tell where someone's looking. And in each story, I'll highlight some key lessons that I learned, all of which helped me develop, I think, kind of best practices for how to make synthetic data and how best to use it in production. So when I started my PhD in 2013, so I'm not sure, which of you guys were in the field at the time. Deep learning, right, was revolutionizing computer vision. It was changing everything, and every field wanted a piece of the deep learning pie. And it was clear that these deep learning models were more data hungry than those that came beforehand. And some PhD students were, very motivated and very eager, like Zukong, and organized massive data collection efforts to feed this deep learning beast. But I was lazier. This sounded like, way too much work. Instead, I was aware of a then recent work about the Microsoft Connect, where synthetic data was used to train a body tracker. And since I had, some ability with 3D modeling, I thought, maybe we could do this for gaze estimation as well. That'd be interesting. So the authors of the Connect paper realized that several key factors were important in making synthetic data work: realism, diversity, and controllability. And these factors will keep popping up, throughout each of the stories we hear about today. So the synthetic images must be realistic enough to cross the domain gap. They must be diverse enough to generalize to the real world. And finally, the system that you create should be controllable, so you can actually make the data you need. Connect was trained on depth maps only, and we need color images for gaze estimation. We want to bring, like eye tracking to the masses, right? With just like a webcam, that's kind of the dream. So the idea is we need to render color images of eyes. And rendering realistic depth maps is one thing, there's maybe much less of a domain gap to cross, but realistic color images of human faces are much harder. In fact, this is the holy grail of CGI for a very long time. So, I said I had some rudimentary ability for 3D modeling, but modeling realistic human heads was way beyond like what I could accomplish. But luckily, at around the same time, early 2010s, photogrammetry, I think, experienced a step function improvement, probably because of a combination of, more affordable, really good digital cameras. So you can get people that have 40 or 50 of these high resolution, very sharp focus cameras, and better photogrammetry software like Agisoft. And the result are scans like these, really high quality, sub-millimeter level accurate 3D face scans. And this is great because you can just buy these. You don't need to be really good at 3D modeling to use them. And they are somewhat diverse. At the time, you could maybe buy about 10 of them, and you get a reasonable spread of diversity. So the main issue is that these weren't controllable. So these scans capture a single instance in time very accurately, but for us interested in eyes, the eyelids have to follow the eyeballs as the eyes move around. So I retopologized each of these scans and rigged it up with blend shapes, like a very traditional computer graphics thing, so we could animate the eyelid following the eyeball. And this is what it ends up looking like, which was not bad. And you can see how the eyelid unfolds and so on. And we got some kind of interesting results using this that were kind of interesting for the time. So the main issues is that it took like a day or so to render all this data on a single machine with the GPU. And we're not actually talking about very much data, only 10,000 images, which is probably considered quite minute for a modern deep learning data set. And like the more data is better, right? Like, how do we get more than this? We don't really want to be rendering for days and days and days. And secondly, with diversity, so we had 10 of these head scans. There's a lot more than 10 people in the world, and they look different. Like, how can we make more people? So the next thing I focused on was, addressing these two problems. So the first one regarding rendering, that seemed quite straightforward. Like the bottleneck is this amazing ray tracing renderer we have that makes these quite realistic looking images of skin with subsurface scattering, and that's nice. But it was a bottleneck, so we could replace it with Unity, which is a pretty reasonable tool to get started with and render hundreds of images every second. So that solves the scale issue. And diversity was a bit more interesting. So we only had 10 of these head scans, and nowadays it's possible to purchase hundreds of these sorts of scans, but at the time only a few were available. And indeed, we're on a PhD budget, so purchasing hundreds of head scans might not be so amenable. So we figured, wouldn't it be nice if we could have out the diversity bit by blending between these subjects? So we did this by creating this 3D morphable face model just of this eye region. So there were lots of previous models for the whole face, very successful, well-used face models, but none really had the kind of fidelity we wanted around the eye region, and none had this separate movable eyeball. So we made a new one, and this was done by bringing all these scans into correspondence and building this kind of traditional generative model. And equipped with Unity and this morphable eye region model, it's possible to render a lot of data. So you just let this thing run, and we rendered like over 1 million images, which is pretty sizable, I'd say. And what you can do is when you have so many images, you can kind of do something like just nearest neighbor match. So you have an input image, and you say, I've got my enormous database of images. What is the nearest synthetic image? And the top rows, you can see the real images, and the bottom row is just the closest synthetic images that matched. I think it's pretty interesting. You can see how you can estimate gaze for input eye images where you probably wouldn't have any accurate ground truth otherwise. So the message of the paper was kind of different to maybe the reality, I think. So the message of the paper was like, more is better. So it had like the word 1 million in the title, right? Everyone likes more. You think like deep learning, more data is better. But there's this figure in it. And if you look at this dotted red line, which I think we dashed red line, I think we kind of made it dashed to kind of try to like hide it. We're like, no, it's the truth. And it's like, after kind of 10,000 images, the signal gets pretty noisy. It's like, is it really helping to have 1 million images? Is 1 million images better than 10,000 images here? I don't really know. And like, there are other things, like definitely you can like find closer matches just by rendering more images. But if you're thinking about just gaze estimation, I don't know if 1 million images helped. And the message here is that infinite is not necessarily better. I think with synthetic data, you often hear this argument, which is like, with synthetics, you can make infinite data. And the kind of suggestion is that with infinite data, your problems will be solved. That's right, infinite is best. But another thing to think about is there are infinite numbers between 0 and 1, right? That's not like helpful. Like you can make infinite images, but if they don't cover the actual testing scenario that you care about, it's not that helpful. So, you know, we didn't have glasses or makeup. And so, you know, having a million images wasn't gonna help there. So it's not just about the sheer number of images, it's also about, or maybe more importantly than the number of images, are capturing the dimensions of diversity in your testing scenario or the real world. And, you know, I've never rendered a data set as big as this again for anything else. Like yeah, I think like 100,000 images is a really good number to get pretty good results with a lot of stuff. So yeah, so following this, I, you know, did some kind of non-machine learning synthetic stuff for a while using model fitting. And that was the end of the PhD. And, you know, for those of you who have submitted a PhD, I'm sure you'll remember, after you've submitted it, you probably don't want to look at that topic ever again. You think like, I'm done with gaze estimation and eyes and eye tracking. And when I joined Microsoft after my PhD, someone asked on the eye tracking team, I was like, oh, you know, are you interested in being involved in the eye tracker? I know you're familiar with eyes in like, you know, in any capacity, not like, I was just like, no, like just no more eyes. Like I'd gone to the point where I couldn't look at someone without thinking about like eye modeling or synthetics. Like looking at someone in the eye was just like, so I needed a break. And I thought hands were perfect, you know, so eyes and hands are both parts of a human. But that's, I think, where the similarity ends. So eyes are kind of like a sphere, an eyeball's a sphere, and they rotate and are not that complicated in terms of shape. The hands, on the other hand, are highly articulate. So a single hand has as many joints as the rest of the human body. And they fold themselves over in weird ways, resulting in high self-occlusion. Eyes, on the other hand, have a lot of complex materials. They're, you know, reflective and refractive, and they have all these tiny eyelashes, which get in the way. Hands are kind of much simpler. Hands are generally kind of naked. And also the HoloLens too, like in the infrared spectrum, hands can all look very similar. You know, there's maybe a bit less appearance diversity in that regard. So, and you know, the topic itself is really cool, right? And especially with the recent Apple Vision Pro announcement, it's clear that other people as well also think hands are maybe the future of interaction. The way you can reach out and interact with digital things just like you would in the real world is a pretty cool thing. So at Microsoft, we had this good hand model fitter, but we needed to initialize and guide it. And so for that, we needed to do some more machine learning. You know, in a, you know, like in industry, there are well-established practices for getting a lot of real data labeled, of course, but even then hands are very challenging because of the self-occlusions and stuff I described previously. So we decided to look at synthetic data, which Microsoft has a long history with. And during this project, we worked on a lot of different synthetic data pipeline. And actually, I think, you know, over the years, we ended up honing our philosophy around synthetics. And so this philosophy has two parts, like how to make the data and how to use the data. So how to make diverse, realistic, and controllable synthetic data. So, you know, scale is still important. We do want to render, you know, a lot of images, maybe not a million. But we're not a fully fledged visual effects studio, as much as I, you know, wish we had one of those with hundreds of artists. We need to do things procedurally. And this is where, you know, parametric models come in, host databases, digital wardrobes, and renderers. So I'll go through them in turn. So enter the parametric model. So this is like the eye region model I showed you earlier. And these things work because luckily humans are all somewhat alike. You know, it's possible to make a function that takes in a bunch of parameters and produces a human mesh or part of a human. And this makes it possible to create human parts procedurally and mix them up together, you know, take one person's pose and replay it in another person's shape. And for hand tracking, we need one of these for model fitting anyway. And this hand model was built from a large collection of hand scans, and we made it look realistic. So it's not enough to generate, you know, static hands, like big open hands. And another challenge is how do hands move? And this is maybe less of a challenge for eyes. Like, you know, it's still, you know, complicated, but, you know, eyes rotate with pitch and yaw, and maybe the eyelid goes up and down. But something like a hand has a lot of degrees of freedom. And so we need to build this comprehensive and diverse pose database. And we captured a lot of these hand poses using a special markerless motion capture system, recording dense point clouds of hands in action, and then fit our hand model to them using this like large offline fitting process. And the result is, you know, thousands, tens of thousands of accurate hand poses. So another thing that, you know, eyes have less of are clothes. You know, people, you know, wear glasses, but you get a lot of clothing that appears around the hands. And this is really important to model. This is harder to parameterize, so I don't actually encourage trying to parameterize clothing. I think people, you know, try really hard to do this. But if you want really high fidelity, it's often just easier to kind of collect a large kind of database of high quality assets and sort of stick them onto your parametric model. So, sleeves, watches, rings, and so on. And finally, you need to render all the image. So this is what the result looks like. And this was the system we actually used to train the hand track on HoloLens 2. For those of you familiar with Blender, you might see the Suzanne monkey in the background. But this wasn't rendered with Blender, actually. This was rendered with an in-house depth camera simulator. So the HoloLens 2 used a depth camera for hand tracking. And I think, nowadays people have realized you don't actually need a depth camera. But at the time, people thought you definitely did. And you can see it's these floating hands, and you get all these nice key point annotations and so on. And yeah, that was pretty useful. And this worked quite well for us. So what was just as important as the data itself was figuring out how best to use that data. And this is something that Andre Karpathy at Tesla calls the data engine. We call it the virtuous cycle, but it's kind of the same idea. So you want to improve both your synthetic data pipeline and your machine learning models. And this only happens once you've got testing in this loop. So you render your data, you train your models, you test on some real data, and then you use those discoveries from your testing to improve your synthetics. And things only get better once per cycle. So the time it takes to do this cycle is how often things will get better. So if it takes a long time, so let's say you render your data and it takes you a week, and then it takes you a week to train, and then, like 2 weeks later, you hand it off to your machine learning engineer, and they come back to you and they say, oh, I found some problems. And then you said, oh, no, you had a bug. And then it's like a long back and forth. So if this thing takes like a month, then your thing's only going to get better once per month. And that can be a problem. So what we realized at Microsoft, we needed to close this loop as tightly as possible. We needed to make it possible that, people could train, test, and, make changes to the synthetic pipeline in a matter of days, ideally. And that is generally possible if you can develop a system where the machine learning engineer is in control of the data they're creating. That reduces this kind of back and forth parsing of things. So it's kind of, it sounds weird, but actually less communication is key. Like sometimes people think like, oh, people need to communicate more. But like the people best suited to solving a problem are those closest to the problem. So if you've got someone, going off to another team and saying, oh, I need this data, and then the data comes back and it's not right, and then they need to go back. This is a long kind of overhead that can really slow things down. So we call this, self-serve synthetic data. And like one example that worked quite well for us is that, or it can be different teams, but as long as they're working very closely together. So we had, so earlier I said hands all look the same in infrared, which is true, unless it turns out someone has tattoos. So tattoos like get very dark in infrared. And we ship some models, and one of the nicest things about developing a product like HoloLens 2 is like when the products start rolling out, like off the factory line, and people start using them, stuff starts breaking, and they get back to you, they file the bugs. And that's so you get a really diverse set of, real test data. And one thing it turned out was that if someone had tattoos all over the hand tracker just wasn't working at all. And so this was fine. And we went to our artists, and so we said that we need some tattooed hands. Within a day they got some texture maps. We re-rendered it. Within a few days we retrained a model. Probably within like another few days, this model was shipped out in a fix. And that was a really great example of when this cycle is working well, things can go very smoothly. So after we shipped HoloLens 2, we're thinking about the next generation of hand tracking synthetics. If you remember, we had these kind of floating arms, which was a compromise because we wanted to have super realistic hands, but maybe we didn't need the whole body. And this wasn't, fully satisfying because we use synthetic data to train the key point networks of the hands, but we used real data for the hand detector, which is like, finding a hand in a full image. So the next step was clearly going full body. And this is much more complicated than just a single floating hand by itself. We didn't have a parametric body model at Microsoft, and I'm always a fan of buy rather than build, and amazing parametric body models exist in literature. So we licensed Simple for this, and Simple has all these great pose databases, and still has a very traditional formulation, very suitable for graphics tooling. So pose database is the next thing we need, right? And although there are lots of amazing pose databases for Simple, sometimes if you have a very specific thing in mind, like hand tracking, these pose databases might not be that suitable. Amass has lots of people dancing or fighting or swimming or running. And actually what we wanted was lots of people poking virtual buttons. And this turns out, even with 2 million frames worth of data, there's not much of this in Amass. So We built a MOCAT stage and recorded lots of these optical marker data, and we use this algorithm Marsh to fit, simple into that. And then it's pretty cool, right? Because you can take one of these poses and replay it on different body shapes and get a really good diversity of data from that. So simple is a great model of shape, but it's not realistic enough for making the training data we wanted. And one nice thing you can do is you can kind of cross this problem by using displacement maps. So we use the same source of scans that we used for the faces, these really high quality kind of millimeter level detail scans. We unwrapped them and applied them as texture maps. And as you can see, can look pretty reasonable. And we did something similar with clothing, inspired by some other work, Simple D, that uses the same idea to model clothing as displacements. And the result is something like this. So, full body animation of hand tracking style poses, which we can then render from a head mounted camera. And that's really nice as well, because where the head is, you can also get a really good idea of, where the head mounted cameras would be. And with a system like this, all of your training data can now be synthetic, which helps, fast iteration and gives you new ways to prototype new devices as well. Yeah, so I'd always wanted to, following hands, I'd always wanted to return to eyes and faces. Eventually, I think part of me deep down realized I'd finally be ready. And when the opportunity came up, that was great. And yeah, something that often makes me chuckle is that people use this Unity Eyes tool thing that was released, and they find use out of it, which is great. And sometimes they email asking, like, "Oh, this is great. Like, how do I get the full face?" I'm like, "Well, it's just a little eye. It's like, there's no face there, but it's reasonable for someone to think there might be like a checkbox to give you the full face. But it's much harder to do. I think, the full face with hair, with clothing, and everything. And this was something only possible, with a team. But again, even though much harder, same pattern, right? Be data-driven, base our work on parametric models, collect pose databases, use digital wardrobes, render it at scale. So parametric model-wise, we used a new one called MOI. And this, of course, Flame is pretty good, but it didn't really have the fidelity we wanted around, especially the eyes, because we did want this thing to be, usable for eye tracking if we so desired. So we built this new one from really carefully cleaned up scans. And I think that extra level of care in the kind of scan preparation helped the model, look a bit more realistic enough for synthetics. And then we collected this expression database using a multi-camera capture studio. So kind of similarly to hands, we used, recorded over 100 people making various extreme expressions. And then we predicted dense key points and fit our model to those key points. And these, gave us around 70,000 sort of expression parameters we can use in our expression database. You can see some examples here. And for, digital wardrobe, so similar idea to before, but now we also have to care about the hair as well. So we built a large collection of static clothing items, accessories, and so on that we draped around the head, formal, informal clothes, kind of like athletic wear, leisure wear, glasses, masks, headphones, other head accessories. And this was like a massive effort to build up this collection over time. And this is nothing where it really helps to have this loop. So you'll train something and you'll know your training data isn't going to be perfect. Like, you don't have any glasses, and that's kind of obvious. And then, you can add glasses, but sometimes it's maybe less obvious. Someone will say like, "Oh, I was wearing this giant face mask." And you're like, "Oh gosh, like, I guess I do have to add face masks to my training data." But again, because you can work with artists, we work with a lot of, we outsource a lot of this to good vendors we have a good relationship with. Then you can get those added to your training data without too much friction. And finally, we render everything with Blender. So this is the the same renderer I used in my PhD as well, kind of evolved over time. So this is the photorealistic path tracer, and this gives us the realism we need and the ability to scale up without worrying about licensing issues. And so the result is these diverse and realistic faces with rich sources of label. And that's the kind of final factor I haven't talked about yet. This is the richness of label. So for a lot of the previous problems, it was just, you just need a few hand key points maybe. With faces, we started exploring much richer, more detailed kinds of label, like the dense key points you saw at the end. So a human might even be able to label hand key points reasonably accurately, though, or with a face sparse 70 key points, they might be able to do that. There'll probably be some errors and noise, but with synthetics, these are perfect every time, right? You get them for free with your render. Obviously, it's still a lot of work to make them, but every time you render, you can get these really good labels. And so with these kinds of labels, you can do stuff like this. So you can train dense key point predictors. And I think here, finally, you can see, us coming back to, eye tracking again. You can predict these iris landmarks, and actually you can track where the eye is sitting in the face quite reasonably, and where it's looking, and what the eyelids are doing. This is also only made possible with some really good model fitting magic we have at Microsoft. So it's the same model being used for synthetics and model fitting makes a really kind of elegant system that is well suited for tuning and running in real time. Right. So, where are we going? So finally, onto what's next maybe. So that was the last project I worked on at Microsoft. So I just want to show some cool work that my colleagues did at Google. This wasn't myself, but I think it's fascinating how computer graphics is a field that's been around for decades, and I think many people think it's fully matured, and yet still in the last few years it's been totally revolutionized by this NeRF thing, and people are finding new ways to render images and generate them. And Jensen Huang said something like, "Soon every pixel will be rendered." No. Soon every pixel will not be rendered; it will be generated. And I'm starting to believe that. And I think things like NeRF and these generative image models will they'll people are already using them together, and we've got to figure out how to keep using them for generating really realistic face images as well. And something like the eye is very challenging for that, right? Like NeRF by itself doesn't model refraction and reflection, but at Google we have these light stages, and we can record really accurate one light at a time kind of data and do some model fitting, and then we can build these special kinds of NeRF that do separate the eyeball from the skin. And get really cool results like this, which I think is pretty impressive. And yeah, as I mentioned earlier, it's really hard to make good synthetic content. It takes a lot of effort, and I think things like stable diffusion will help make that easier, I hope, or more. You'll make it easier to add controllability and diversity to your data sets, perhaps. And finally, I'd like to show off some of the work we've been doing at Google in our team. So here are some of the faces we've been collecting. So we have a large data collection effort at Google to really try to understand how faces move, what they look like, to really try to model the diversity of the human population in all its regards. And so here you can see some face registrations where we capture the lip motion, and there's no sliding over the skin. And this is the sort of source data which we can use to make new generations of synthetics that achieve like a really high degree of detail and fidelity, like some of the stuff you see here. Yeah, I'll just let this one here, little performance question there for you. Right, so to end, I think there are kind of two lessons I want to go back to, and that's this. I've been repeating this kind of pattern over and over again, right? So this is one pattern that's worked quite well, and there's many different ways of using synthetic data. Like many people use these kind of static scans very successfully, like for PyFu. But for many of the problems I've worked on, this is a pattern that's worked well. Starting with a parametric model, building a post database, building a digital wardrobe, and rendering it all procedurally at scale. That's how to make the data. And then maybe more important is how to use it. And it's one thing, if you can make the data, that's okay. But if it's not being used, if it's not useful for someone, that's not great, right? And so with that, it's this data engine or virtuous cycle that's incredibly important. That's this, you must make sure this loop has as little friction as possible between rendering, training, testing on real data always, by the way, like if you want to get useful insights. And then tuning or improving your synthetics. And once this cycle becomes really, really smooth, you can iterate very fast and accomplish some really cool things. So yeah, thank you very much.
Okay. Thank you for the talk. Any question? Yeah, for some of the big synthetic models, where you could explicitly model the eyelash geometry. I know a lot of approaches use like custom shaders for a lot of the face on it.
Yeah, I think we model eyelashes in a variety of different ways. I think in real time we modeled them with cards because it's like we wanted it to be rendered faster. But I think it's just actually, I moved away from real time renderers, maybe partly because as I moved into the industry, it was, we had different tooling, like with the HoloLens 2, we had a very custom renderer. So and when you're rendering offline, you can use strand-based geometry, and I think it adds a lot of realism, especially for super close-up renders. Like when your camera's really close to the eye, you do want the strand-based geometry to model how light scatters through it. Like if you have some lights very close to the eye as well, you kind of want that light bouncing around inside the eyebrows to cross the domain gap. Yeah.
Like if we use this parametric type model, so there are several hyperparameters based on the person to person. How do you handle those kind of like body size, hand size, something?
Yeah. So the good thing with parametric models is it lets you be data driven, and this is key difference to an alternative might be you say, oh, go to TurboSquid and find some hand models and get the technical artist to try and animate them. But I'm not a fan of that approach because it doesn't let you be data driven the way you can be with parametric models. In general, I kind of just like to replay sometimes it's if you can just replay an actual performance, like this is someone's face geometry with we're not mixing kind of poses and shapes. But I mean, other times you can do that. You have to worry about things like if you change someone's body shape and they're doing some if they're touching their hands like this, then if their arm gets twice as long, you might get some issues. But I mean, it's very case by case. I think you have to figure out what you can get away with as you're adding diversity. But as you collect more and more data, you might not even need to mix it around that much. Like if you can capture a lot of data, you maybe just can replay it and get your perfect labels, and that is good enough. Or maybe slightly perturb it, change the neck angles just a bit to get some diversity. I think it's very it takes a lot of judgment to tune these systems, unfortunately still. but all, as you say, there's a lot of levers. All the levers are there, and if you can get into a situation where it's quick for you to render and then look at your results and then maybe train with them, you can do some kind of small sweeps to see what works best. Okay, sorry.
So I wanted to ask a question about the result light falls on the eye as well as on different parts of the body. How do you model like different light environments? For example, if it's a very light environment versus a darker or more light environment?
Yeah, so for faces in particular, we kind of, I mean, for images like this, which are a bit further away, we use high dynamic range environment maps, which are really easy, it turns out, to get online. There's great sources with permissive licenses, and they model strong light very well. And how an eye actually looks in that lighting environment is, that's a good question. So we try our best to model the materials quite accurately. With something like eye nerf, this is all this has come from the actual capture light stage itself. So we have this one light at a time system where it'll fire a lot of different lights, and you can then do a lot of math and figure out how this surface reacts to lights from different directions. But otherwise, it's more sort of traditional CGI of trying to say, well, I know the iris is this refractive index, and we roughly know the skin behaves in this way with subsurface materials. So a lot of it is maybe more artist-based, and that's not something we should shy away from necessarily. I think as scientists, we're very tempted to be really data-driven the whole time. And I just answered another question saying it's important to be data-driven, but also I think balance is important. It's also important to realize that sometimes the right call is to kind of just eyeball it, like pardon the pun, and just say like, okay, this looks realistic enough. Because I mean, artists have been doing that for thousands of years, right? It's like I know Michelangelo didn't. Well, maybe he did, but I think probably there was a lot more eyeballing and just kind of art going on than collecting. Yeah, this is overloaded term a lot.
So there's a fair amount of evidence that when a human estimates another human's gaze direction, that they're mostly using the eye area just to get gaze direction relative to the head, and then they're using the head to get a more absolute direction. So I'm curious what you see when you add do you have a sense yet of when you add the head to your data, what happens with the eye gaze estimation?
Yeah, good question. I think it is important to, to treat the head as a whole when you can. And I think we've seen that in the field as well. More and more approaches are just doing just that, because you get a lot more information from the whole thing. And I think at the beginning, also maybe because of the tools available to us at the time, people were just focusing on these small eye regions. But when you get the whole head, and I think we see this a lot with the kind of model fitting stuff, it really helps just seat the eyeball in the right place, because sometimes from just a small image, you don't know where the eyeball is, like half a centimeter up or down. But if you get the whole kind of face, you can then get a better estimate for that. Especially also if they look around during a sequence, you can kind of optimize for that as well, and that will help you, I think, get a better eye gaze.
Okay, the last question. Sorry.
Have you ever noticed any need for the main adaptation?
Good question. I think we do domain adaptation, but maybe not in the way that is often seen in the field. Like, so all of our images that we render are, people would say like generally, come on, get over there. Like, oh, they're too perfect. This is a common argument. It's like synthetic data never works because the images are too perfect and they're not like a real world image. And that's why you must mix real data in. The most success I've ever had is never mixing in real data and not actually using these kind of machine learning forms of domain adaptation. But of course, we do a lot of appearance augmentation at training time. So like a very, very aggressive augmentation strategy is used. Loads of, the standard stuff like hue, contrast, JPEG, blurry, motion blur, noise, grayscale, I don't know, like, all that stuff. And that is a form of domain adaptation in itself. And that's how we go from these, perfectly crisp, perfectly color balanced images to the sort of like awful images you get in the real world. But I've not used a learning-based method for that, mainly because, well, two things. One, that I'm worried that it will change the semantics of the image too much, like it'll move around an eyelid by a few pixels. And actually, one of the main strengths of computer vision of synthetic data is its perfect labels for training models. And if it changes the semantics, that's an issue. And secondly, I think because it's a distraction. If you might think, okay, it's not working, what do I need to do? I could improve the synthetic data, or I could try to train some domain adaptation thing. And I think the best investment is in just improving your synthetic data. Like, you can render photorealistic images with good diversity, and that's what you should focus on. And as a team, you've got a set amount of resources. And if you try to do domain adaptation, I think it's less valuable, and it then doesn't generalize to a new project. Let's say now you've got a new camera or a new device. All your domain adaptation maybe is no longer that useful. So that's why I've kind of always pushed for a different approach.
Okay, thank you. And let's thank you,
guys very much.
Erroll, for the